Right, you want to get started? Yeah, sure. Okay. Hello, everybody. Okay, I think we're gonna get started. Manu is going to be a few minutes late, but I thought that we could talk a little bit about the Fred Park assignment and the table that we went over on Tuesday. Are there any questions or thoughts, concerns? Has anybody thought a little bit about what problem that they want to work on? Yeah,
I guess I was probably just gonna do the same numbers on it.
okay,
It's like for access in the US.
yeah. Healthcare, okay, healthcare access in the US. Did anyone on Zoom also think about healthcare access in general?
Yeah, I would also like to put that in this regard, you can think of developing a simple diagnostic or early diagnostic for sepsis after COVID infection. It we could do such diagnostic test by bedside manner.
So sorry, Tathagata, I think your audio is a little was cutting out. Yeah, so while he's fixing the audio, maybe someone else could
Yeah,
share. Oh,
is it better now?
yes, yeah, a lot better. Yeah, go ahead.
Yeah, so I am also thinking in the same line uh, to to basically um, to give a better access of the diagnostics to different range of people, or let's say different stages of healthcare, like
Mhm,
developing a very um, cheap diagnostic test for early detection of sepsis. We can use I mean, in this project, we can use paper fuse that is developed by Professor Manu's lab for
mhm,
the plasma and blood cell separation, and from the serum we can uh, try to detect bacteria or viruses as low as possible. That could help us to indicate a very early stage of sepsis, and that
mhm.
eventually could help managing it in a better way.
Nice. Yeah, so you're thinking specifically about sepsis. Is that in neonatal sepsis or is it for a different age group?
Okay, I was thinking, as of now, I was thinking in a very general manner.
Mm,
Yeah,
okay.
to, yeah.
Yeah, awesome. Thank you for sharing.
And
Lucas.
also for the sensitivity and specificity of detection, we can use CRISPR technique as well.
Mhm.
That I was thinking in that way.
Yeah, awesome. Thank you. I
Mhm.
just wanted for Lucas, was there a specific part of healthcare access in the US that you were thinking about?
Yeah, I guess I was just curious because we talk a lot about healthcare access like globally. And
Yeah.
so my by the numbers was about like how like a lot of the US also forego like US citizens
Hmm.
forego medical care because of costs.
Yeah.
And then one like area that I was kind of interested in like honing in on was healthcare literacy. So
Yeah.
like if people are unfamiliar with how the health system works and how the
Mhm.
health insurance like can cover things, it leads to them to be more likely to forego medical
Hmm.
like procedures that are necessary
Hmm.
because of fear of cost, even if they
Yeah.
would be covered. So I was kind of thinking about how like health insurance changes.
Yeah. Okay, so what Lucas was saying was that um, he was interested in healthcare literacy in the US because even in the US, some people forego healthcare because of costs. And so that is a really interesting angle at it. I like it. Tushar, do you want to go ahead and share what you were thinking?
Yeah, I was going to say what Lucas just mentioned about not just the healthcare access, but the literacy that people have around healthcare. So a few observations that I wanted to say was like two like one on literacy and one on access itself. So first of all, talking about literacy, I've made certain observations that there are some people who reside in some remote areas, since they do not understand the diseases that they have, the problems that they have, and the healthcare or the services that they're receiving. Like what happens is some things go wrong, because of which they lose the entire trust from those people. So I talked to one person a few weeks ago. Like they were from the remote area, and their father got COVID, and they went to the hospital of the remote area, and they gave some medicine. The person died, and they started thinking that the vaccine and stuff, those are not good for people. So it gave them that perspective on medicine. Then the second observation was on the access itself, which was again, in remote areas, what happens, a lot of people, they tend to at least the women, when cooking food, they tend to sit for long hours, right, when doing dishes. For a lot of home stuff, they just sit all day and work, because of which they develop issues in the knees and stuff. But since they do not have access, they cannot get those treated, and so they develop a lot of problems, because they cannot even walk properly or climb stairs and stuff. So again, they do not know what the problem is, first of all, and even if they could know about it, they just do not have access to go and get it treated.
Yeah. So I'm curious, when you talk about knowing what the problem is, or even just the broader term of healthcare literacy, what are some things that you can measure? How do you quantify that? Anyone can answer this, but I'm just curious what you're all thinking.
Yeah, hi. So I'll add on to the to search point. So I was involved in a Indo-UK AMR project. So in that there are different segments. So there are people from social science also. In India, I'm not sure. There could also be in the other countries. In India, the primary healthcare is a large portion of the primary healthcare is managed by quacks. So they are basically untrained doctors. So I'm giving a very simple example that could be measured. Let's say someone has a bacterial infection and due to cold, and antibiotics has been prescribed to take for 5 days. Let's say some antibiotics, so let's say azithromycin. After 3 days, the person starts to feel better because some of the bacteria has gone lower in the tonsil. Most of the cases, the person stops taking the antibiotics. So it was a 4 day or 5 day course. The patient usually starts and basically stops taking the antibiotics after 3 days. So what happens? That leads to a development of AMR in the body itself, and also the antibiotics are disposed in a very non-scientific manner. So basically they just throws the antibiotics into the dustbin, and it goes to the environment. That also leads to development of AMR in the environment. So it's a very simple, I mean very wide scale problem, and that could be measured. I mean, the number of days antibiotics are taken, and also that could be the literacy could be increased by some apps or like this, because people are not aware of the problem of the AMR, and everyone actually takes antibiotics. So
Yeah.
yeah. So this is one of the problem that I came across through the social science people. Yeah.
Yeah. So that's a leading cause of antibiotic resistance as
Yeah.
well. Yeah.
Yeah. In
And
India,
so,
actually, antibiotics are available over the counter. So you can
oh,
purchase it without any prescription. So
I see.
that magnifies the problem as well.
I see. So there's also part of it is patient compliance, part of it is also possibly regulation of certain
Yeah.
pharmaceuticals. And I guess there's a lot of different aspects that you could go about this. So
Mhm.
Manu is here.
Can you guys hear me?
We
Yeah.
have
Sorry for being late. I ended up, I wasn't in the crash. There
Oh,
was a crash on
no.
280. I guess it's raining enough.
Yeah.
Somebody should solve the
You
tire
can put
problem.
this on.
Can you all hear me?
Yeah.
And again, sorry for being late. Thanks all for folks that are waiting. I guess we already did the Fred Park discussion, right? Okay. I think it's very important that if you have any clarification, because we'll be building projects on that. So this would be the time if you want to know something a little bit detailed about it. We're going to switch gears today a little bit and do, so far we have touched upon health as a little bit of a challenge. So at least some of you are motivated. How many of you are thinking about health-related project, by the way? Okay. After today's class, my hope is that some of you would want to do a climate-oriented project. And it might turn out that plenty of problems are actually climate and climate change oriented. So there's a huge amount of overlap in that space. And then in a week or two from now, we'll also just cover more of a broader spectra and one or two problems in the education space. I think this is just to provide flavors so you feel that any direction you want to take, as long as the principles that you apply are the same, it's perfectly okay. So let's talk about the ocean today. And is there a simple way to connect? That's the right way to connect, right? My screen.
You able to join the Zoom?
I can join Zoom. Yeah. That's trivial. Do you know where that Zoom link is? Which link should I go to? Do you know? Oh, just ours
just
or
in
you
the
and Rush?
chat.
Got it. Oh, and then do I join the audio or not join the audio? This is running through.
Recording in progress.
So I mute myself here and also kill the audio here. Okay, perfect. And if I do that and share screen, oh, this is fantastic. I can sit, I could have joined from my car, and that would not be actually such a good idea. Okay, thumbs up if you all can hear me online. And I'm going to walk around a little bit. So from time to time, if folks are monitoring, you can see if you have any set of questions. So I think there's a lot of general things that we can say about our planet. Maybe what we'll try to do is choose maybe one or two verticals to do a little bit of a deeper dive. The idea here is that you could spend a lifetime trying to understand the ocean. That's why I call it the great unknown. And so I'm not, the teaser here is for you to appreciate the depth of problems that we have. And then eventually I'll do this on a more personal basis, because almost for the last 6-7 years, I've been going out on expeditions at sea. And that's really converted me into thinking about why all of us should be thinking about the ocean. So, there's a lot that you can read about that I'll just skim over. And actually, let's just start with a framing of just what does it feel like to be at sea? So I'm just going to flip this around a little bit. Let me tell you the first time I went to sea. This is the vessel that I was on. So maybe step back. Has anybody been at sea? Like truly no close to land. Can you describe why, how long? Okay. How long were you out? Okay. And which coastline, which currents? Uh-huh. Yeah. And then which vessel was this? Yeah. So, and this is a teaching vessel, right? Yeah. Uh, that's phenomenal. Anything you remember from being at sea? Yeah. Just what do you want to share? What is the most profound thing that you remember from that experience? And then I don't know if folks can hear online. I'll try repeating it otherwise. Yeah. It's a tough question. Yeah. And that is what I'm trying to evoke for all of you, that without being there, it is hard to understand what it means at sea. Mm-hmm. Mm-hmm.
I miss forest, but I miss mountains a lot.
Uh-huh.
But it also the movement at sea is like a big collaborative process. You can't really pick up home.
Mm-hmm.
And I think it's probably one of them.
You don't choose to go wherever you want to go. Yeah, that's true. Uh-huh.
And even if solar sailors are like depending on like habit
Mhm.
to get somewhere, which is not always the same thing that is visible or is immediately apparent in terrestrial.
Mm-hmm. So if folks heard it online, and I don't know, maybe for folks that are connected, has anybody been at sea before? If you have, just raise your hand. I would love to hear. I don't see any raised hands. And I don't mean going to the beach, which I'm assuming all of you have, right? Yes, almost. Okay, I see a hand. Do you want to just describe what was your experience like being at sea and where were you?
So me, you mean?
Khan, yes. Yeah, I see your hand raised. Yeah.
Actually, I coming late, so I'm not sure what is the question you mean. But
Oh, the
that's
question is if you have ever been at sea.
yeah,
Yes.
yes.
And where?
Oh, it's actually I have been at sea, so my house near the sea.
I see. I see. Some
So
of you
every
some of you
week,
grow
so
up close to the ocean.
yes, every week we came there, and
Yeah, I mean, that also counts in some sense because it's a different experience. But for some of the problems and challenges we'll talk about, there is a kind of an experience that you can have. So this is Kilo Moana. It's one of the research vessels owned by the NSF or owned by the US Navy, given to NSF for research. It is part of what is called the Ahola Hot Time Series. It's the longest oceanographic time series that goes to Point Aloha, a very specific point. I'm trying to remember, maybe 300 miles or so above Hawaii. And it goes there every 15 days. And it's been doing that, I think, maybe for 20 years or something. And it's the longest continuously running time series. Of course, we will talk a lot about time series. So we were part of that time series just while during that transect, we were trying to deploy instruments and just thinking about the sets of challenges of how to study. And I think one of the important parts to remember, at least my personal experience of being at sea, is how small we are. There is nothing to compare you to other than just the vastness of the ocean. And since it's only a coincidence, just Tuesday we talked about plastic and everything. I mean, this is one of the key challenges that in terms of the scale of the ocean, it's just really hard to grasp. Even when you're making measurements, even when you are thinking about a problem, and then also just physically when you're there. It's incredibly heterogeneous. So when you do a transect, immediately conditions might change and you would see a totally different part of the ocean. Since that time, we really started spending a lot of time at sea. This is what it looked like 2 hours after I had just woken up. We were running some experiments, and then you'll give a kind of a sense. Uh, so we had to shut down operations. There was a massive storm, and the entire cruise, it's very rare for them to cancel a hot cruise because that will be an empty data point in a 20-year time series. But it was not safe enough. They turned the boat around. Whatever we had to wrap up and go back home. That happens all the time. The last Bermuda trip, very similar situation, just the weather ended up being way too out of control in some sense. But one of the other parts of this framework, when you're thinking about, for example, networks like these, and we'll talk a little bit about what are we trying to measure, what are we trying to do. The other thing that I remember taking away from this was a realization of how expensive it is to do science at sea. This is frugal science, so cost is always on my mind. Do you want to guess how much was I paying from my grants, not from my pocket, per day to be at sea to do operations? If you actually paid the bill, then you have to wait. I think you might know the answer, but I want you to just get a sense of, you have an intuition for rockets and space explorations to a certain, how much do they think we pay to be at sea per day? Yeah. Yeah, so close to around $60,000 per day, Yeah. No, sorry. The whole crew cost, it includes the cost of fuel. Massive cost is in the fuel. Much of the cost is in the infrastructure of the crew that keeps us alive. So it's a 10-person science team, 10-ish people, crew members, boat operations engineers, people that actually operate the entire boat, all the marine techs. But we go on expeditions that are 40, 45 days regularly. And so the last one we did is in the Arctic. And maybe I'll show this one picture from that Arctic trip is actually worth seeing. What might be the place I might. It is worth digging up that picture. So that's the last crew from the Arctic. And again, the challenge is. Oh. Can you all hear me now? So
Yes.
what's going on?
Someone just said yes.
Oh, I see. I was like, I didn't even say yes. How can my echo be yes? So one of the challenges that we'll talk a little bit about is, to a certain extent, dramatic things are happening on our planet. The spot that you see here, you hear about it in the news all the time. This is a picture that we took from a drone. We're all on that boat. Some of us are on what is called a bear watch, because we're running operations on ice, thin ice. And of course, we're all scared of the bears. So one person remains on the boat with a gun to make sure that a bear doesn't come and take away your equipment or actually take you with him. So it's a fair risk, and we did see a couple of bears, and I'm not going to spend too much time on, but when you're trying to understand the planet and you're trying to understand climate per se, there are these counterintuitive things. First, you have to be everywhere all the time to really make the measurements. And most of the places really on the planet, a significant portion of the places are not so habitable and so comfortable here. So the amount of infrastructure that it takes to get there is actually quite difficult. So this, this place, why is this place important? On our planet, currently, it's the fastest temperature rise is currently in the Arctic. So, we worry about delta C that you all hear about, these sets of scenarios. The poles are just astronomically faster, just because it is kind of a heat engine associated with how it absorbs heat. And so, of course, the ice is melting rapidly. Most sets of models talk about the idea that we will not have ice cover by the time, I would say, 10, 15 years from now. So in the summer, yeah. Good. Everybody ask for that. Yes. So these icebreakers cannot go, they only can go in 1 meter ice. So this is actually very, very shallow ice. And one thing that happens is this is the ice that forms and regrows every year. But then there is what is the permanent ice. And that's really, starts 5 meters and onwards and much, much thicker. And most of these ships can't go there. In the old days, like just in terms of latitude, longitude, this latitude we would not have been able to reach with this vessel to begin with, because it's only capable of traveling in this very, very thin ice. And so in some sense, you can think of it as a flux around that's always going on. And then there is a reservoir. And what's happening over the time is just the reservoir is actually melting. And I think I have a video of that somewhere. I'll pull up and show in a second. Yes. Yes. It's very difficult. And the types of expeditions that go on land occur, they're very different class of expeditions. One way to do it, and again, going back to cost, and I want you to think about cost in all of these types of things, because instrumentation and ideas could completely change that, especially where humans are not involved, if you could automate some of these things. There was an expedition that happened during the COVID time. It was called Polar North or something, where they took the boat and they froze it and stayed throughout the year. That's very dangerous because nothing can come to rescue you. No vessels, no supplies, nothing. And there you just let the ice grow back. But you could imagine, and this was the only expedition of this kind at this scale, where they literally froze an entire boat at sea and kept it for the entire polar, just a year. So most of the time, all our observations are in the day. There's only day. So there is no night during that time in the summer, but they also are observing what happens in the dark. And that is actually thick ice. There are instruments, and you can make ice cores and all that related with those sets of scenarios. That's one way of doing it. And then the other way is, there's a lot of work, for example, that happens in the other polar sea, which is in the Antarctica. There, it's different. There is permanent land. There are ways to land airplanes. There's a lot more infrastructure. There's permanent infrastructure there. So a lot of programs that we work with, for example, partnerships, we can deploy instruments. And one of the instruments that you'll all be playing with, which is the planktoscope, tomorrow, we have one of them in the Antarctica right now. And so exact same instrument is continuously operating at a permanent station in Antarctica. There are no permanent stations in the Arctic. There is a proposal by the Tara Foundation. Actually, it's since you brought that up, I'll show it to you. It's a crazy idea. Tara polar ice. I'm hoping that there is a public. There it is. This is not real. It's somebody's cat drawing. And what's quite amazing about this as an object is it's being thought of as left to embody and drift with the ice while you have a port at the bottom. So you also have access to water. But, unlike the idea that on a research vessel, at least you can move around. If you plank yourself in ice, you're just an anchor point and the ice floats. So it goes wherever it goes. There is absolutely no control on your GPS coordinate system. So this is a proposal. I think my hope is that it gets built one day, but currently it remains as, there's a lot of discussions and design teams that we've been in conversations with, but one of the challenges around this is a station like this doesn't exist as yet. Was there a question? Yeah. While I'll show you guys other boats also in that. Yeah, go ahead. Mm-hmm. Yeah. I think there is a ton of technology that gets ported from the space program in our daily lives. And similarly, you could imagine investment and growth in expeditions from a planetary scale, especially in oceanography, that you might be using in our, say, water supplies and all kinds of other stuff. You know, the satellite communication, for example, for all of this, the fact that currently I can, even when I'm at sea, I can do a Zoom lab meeting, which we have done a couple of times. We have satellite connections. There is a lot of commercial technologies that can now make possible and reduce the cost of these expeditions. So the one big thing that I just wanted to start with is, I brought up the cost point, but evoking a sense of wonder about a subject that you're thinking about is important as a fuel for your curiosity and the effort. And so, these sets of pictures are just, I'm always, even when I'm not at sea, I look at these pictures sometimes because I feel like, I wish I was there. And also it kind of reminds me of our limitations. We spend and build a lot of time building a lab very quickly inside. So we would operate and work in these lab stations. All the assays that we need to do them there in a transient manner. And then I'll talk a little bit about why we are doing any of this to begin with. But kind of the more personal note to show and share. So, it's the last 5 years, that's the number of expeditions that we have been part of. Some of them are coastal as well, so they don't all have to be incredibly exotic. Some of them are, you can immediately get started. You can immediately, the kind of resources that are needed are not the same. But I think all of them are gearing towards going back to what I wanted you to sort of think about, which is the context of what I said, the great unknown. Having done this for the last 5 years and just in general from where we stand today, there is a tremendous amount of what remains unknown about our oceans. And I think that's kind of, I'm assuming you have read quite a lot about the importance of the ocean, but often enough, it is not conveyed how little do we know. I mean, everybody likes to quote this idea that, oh, we know more about the surface of the moon than the bottom of the surface of our ocean. That is technically actually true. Somebody did do that calculation that just sonar maps are not high enough, so we have better resolution maps on some parts of the moon. But we're not even scratching the surface because moon is a barren rock, while the ocean is a living ecosystem. And life dictates all aspects of this water body. And so in terms of, I get really scared as a society, we're thinking a lot about engineering our oceans. We're thinking about how to utilize its capacity even more. And I think one important thing to remember is currently, most of you have seen the absorption of, emission of CO2, I'm assuming, right? So let me pull out that plot for a second to show you ocean capacity to absorb. absorb CO2. This is a very classic plot like the Keeling curve that is worth seeing in its entirety. And it's a really beautiful plot that I remember. If I can't pull that, I'll just try drawing it in a second. So for example, the total amount of CO2, actually, this is maybe one way of looking at it. Although I would, okay, I think maybe that's the, no. There it is, okay. I really want you to just, we'll walk through this for a second. So again, going back to by the numbers. So everybody talks about the top curve, right? We all know and understand we're pumping a ton of gigaton of carbon in the atmosphere, right? One thing that's very interesting at the bottom is the inverse, that there are processes on our planet. So you know how many tanks, for example, or barrels of CO2 we consumed last year, because everybody is monitoring it. So you can look in and you can find out exactly how many liters of fossil fuel we burned. But that's not what is in the atmosphere. We measure what's in the atmosphere, but some of it goes somewhere. And then when we look at the evolution of what happens is, by the 1960s, when we were, say, pumping maybe around 3 or so gigaton flux in CO2, you can see a portion of that, this portion was getting absorbed by the ocean. And only, this is what we're pumping. So this is the positive, and then this is the negative. This is called the carbon budget. And you can start seeing that as we started pumping more CO2, the ocean started taking more CO2. And this is the biggest mystery currently in our planet in terms of climate models. And we don't understand the processes at which somehow the ocean is helping us. It's decided, I mean, it could have gone the other way. It could have just said, no, that's what I'm going to do. And I'll talk about this process of how the ocean actually takes up CO2. But it's quite remarkable that this, of course, keeps rising up only because this is not increasing at the same rate that we decided to pump CO2, right? So you can see that it's a very delicate balance. And all of that is really associated with the fact that the ocean is a living object. And you have to understand these processes in great detail. And this is what scares me the most, is that at some point of time, not only are we not slowing down, that these slopes have feedback loops that are much more complex than we understand. And then this relationship will break down. It's unfair to say currently that we should just draw a straight line right here and say, hey, look, if you don't understand this process, this could really be a nonlinearity, which is, it's classically called tipping points, that there might exist this tipping point that after this process, it has that much capacity, either it flattens out or it actually just stops to a point where, because the living ecosystems that are making that process happen, and that would be an absolute catastrophe. I mean, even its flattening will be an absolute catastrophe. And so I think, this is at least personally, when I'm thinking about the ocean and why we go out to sea, is really trying to ask ourselves this question. It's a very fundamental question in some sense. It's all based on measurements, and we'll talk about what's missing in the measurement. But really, if you remember try to keep this in mind. And again, this land sink is another very important source, plants, many other factors. But if we keep removing land to play a role as a land sink, then also that becomes a problem, because with urbanization, that footprint is also very nonlinear. There is no one-to-one relationship with the number of trees that you plant and the amount of CO2 that would effectively actually truly take away. So I think this is the complexity when I'm thinking about an ecosystem that we know so little about. This is sort of what keeps me up at night. Is that relationship intuitive, or at least the puzzle is intuitive? And then we'll talk about where does that come from. So I love this kind of an animation. I'm going to see if that, it is an animation. What happened to my, that animation is worth playing. Let's pull out another deck on okay, that was a polar bear, by the way, that does visit. This is our anchor point for our drill, and it came by, hung out for a long time, and not fun. Fun to watch, but not fun, actually. Yeah, scary otherwise. Okay, so I think there's a animation that I want to show you guys. This is one of the best models that we know so far that tries to incorporate the idea that the ocean is a living ecosystem, which is, so this is a simulation, first of all. This is called the Darwin Project. It is doing a grid scale simulation, and the colors here are from the satellite. So you notice seasons are changing, and the green in Australia is growing and shrinking. That makes sense. But what's plotted in the ocean currently is essentially plankton density, or chlorophyll density, lots of photosynthetic organisms, and you start seeing this massive dynamics. And some of it is trying to mirror what we see in the satellites. So there is a tremendous amount of burst of growth that happens. Things die. There are patterns. You will notice punctate right around there, and you can guess that there is a major city here, and it's pumping a ton of efflux and its waste that acts as nutrients, and that leads to these massive peaks of organic matter and life in the ocean there. We can look at our own California current in a second. Oh, come on, I wanted to rotate a little faster. Oh, now it's not rotating, sorry. Where is our California current? Right there. So you can see a massive amount of eddies, and again, a ton of, because there is a lot of upwellings in this area. But one of the important things to understand is all of this is also just the surface, by the way. And the ocean is not just the surface, it's 4 kilometers deep. So we have no intuition for how biomass is truly distributed in this spatiotemporal way volumetrically, because the best measurement technology that we have so far is satellites. It only measures chlorophyll only when the clouds are clear, only at a thin layer of a water film. And because life is distributed volumetrically, it's not so obvious to say, hey, I'm going to just multiply that by the depth of some kind. That's what we currently do, but it's a very difficult proposition. And that's why you actually have to go to sea. Yes?
So they train the model based on satellite data.
That's correct.
So this is that data.
Yeah, because we can't image the satellite data at this resolution continuously in that dynamics. So they train some of the model. This has the hydrodynamics built in. I mean, it's a beautiful model. If people are interested, to take a look at it. It's in a 30 by 30 kilometer grid. It has different categories of organisms, hypothetically. They have a nanoplankton category, microplankton category. They have a grazer category. It is running these predator-prey simulations to see if something increases. it doesn't have sedimentation, which is what I work on as a lab, where we're trying to understand how most life is heavier than seawater, so it sinks. So it doesn't have much of the sinking dynamics of the life itself, so it doesn't truly map what's happening. But again, actually understanding this model, if somebody gets interested, is fairly simple. Like the original paper that this is built on is a very, very cleanly written model. And for folks that are just interested in modeling per se, this is a beautiful paper. Not the final version of the Darwin project, but the original paper that modeled it. That came out from the Gulf of Maine model. Yeah. Yes. Uh-huh. Yeah, I mean, great questions. So of course, light and the amount of light matters. So that will be true. Nutrients, there's incredible amount of upwellings and currents that are dictating, because a lot of life and organic mass, and I'll connect the two of why life at sea and this carbon sequestration are two connected ideas. But the dynamics of the ocean drives that. So nutrients, there are dead zones at sea where there's plenty of light, but one key nutrient, like say silica, is non-existent, and diatoms are the most abundant, for example, in that ecosystem, and then boom, you can be there for as long as you want, and you see a massive depletion. No, there are very limited oxygen zones sometimes. You can end up in these packets. So one way of thinking about the ocean, it's actually quite heterogeneous. It is not a bathtub. It's not a well-mixed. Neither is it well-mixed vertically, nor is it well-mixed horizontally. And this is why people worry about when they say, oh, some of our currents are about to be diverted, because they might actually realize the fact that if that current gets diverted, all of this dynamics would change. One thing that you said, it reminds me, one of the reasons, and with Kevin Arriago's lab, when we do kind of the Arctic expedition, 10 years ago, they noticed something quite strange, is that the ice was thinning so much that for the first time, they saw the highest density of phytoplankton and diatom life that they have ever seen anywhere in the world, which is bizarre because under the ice should be dark if the ice is thick enough. So it went from being a place which was just dark, devoid of photosynthetic life, to being the highest density ever recorded, tenfold higher than anything that had been recorded, only because the ice thins. So when you're thinking, so enough light can penetrate now diffusively through this thin ice, and then there was plenty reservoirs of nutrients and there are all kinds of explanations. People still don't completely understand it. But it's an important thing to kind of try to remember, that why should we believe that the ocean can change when we look at a rainforest? If you go to the Amazon every year, completely different, tiny amount of development, new things take over, certain populations completely disappear, new species arrive, new plants arrive. So the ocean is as dynamic in some sense. And this is also one of the challenges associated with the carbon sink models per se, because we're not accounting for any of the changes. So just going back to numbers in some sense, I think this is an important thread to think about. The ocean is absorbing currently around 93% of the heat that we kind of emit as a planet. It is really a thermal bath, right? And that's why the polar ice caps are important, because warm water goes out there to cool down and then come back in. And so in terms of general ocean temperature, surface temperature. But what's very important is between 50 to 30% of all CO2 that we are emitting as a society is currently being absorbed and permanently sequestered by the ocean. That was that blue line that was rising. And the worry is that we don't understand where that comes from. And we don't really have, I mean, we have a term for it. It's called biological pump. And the idea is, and I'll describe the pump in a second, The idea is that if somebody was to turn off this pump, it's unfortunate. I made this slide some time ago. Does anybody know the current number? We should have a counter, like just next to a clock, a running clock. Okay, let's check. What is the current CO2 in atmosphere? 419. So I made this slide several years ago, and you should all remember what was the ppm that we were all born at, because in the end, that's like a ticking time clock in many a way. And I mean, this is really about a budget, so I really mean it. So if somebody was to turn this mechanism off, it would jump from 400 to 600 immediately. That's the level of, just because the amount of absorption that it takes, because that budget would just get added back in between 30 to 50%. Yes. Absolutely. This is something we can't do anything about, but that's what's happening. And there are secondary effects, which is that if there is dissolved CO2, and we'll talk about the mechanism I'm talking about is actually a true sequestration mechanism, that it truly takes away, that the CO2 is not in dissolved state, but simultaneously in equilibrium, the dissolved CO2 is also higher, because atmosphere and dissolved CO2 have to be in equilibrium. So we are making the oceans acidic, and at that same time, there is a secondary process that is constantly trying to pump. So, I think I want to tell you why the ocean is an incredibly important part of our lives that you should all think about in terms of projects. Anything you can do to make measurements at a lower cost in the ocean would have a tremendous impact. That's kind of the overall message. And we'll choose now a few examples of what has been done, what improvements could be. But I think, this is a big picture. Again, a depressing picture to remember, but all the more important for why I'm hoping some of you will end up choosing oceanography as one thing to kind of act on. Let me just jump to I think we discussed a ton about the plastics. So, I think I went back and what I miscoded myself. I said 90% is missing, and then I went back and looked at this number and I was like 99%. So anyway, but we talked enough about microplastics. We're not going to spend too much time on. I did mention to someone, I'm going to try to remember. Yes, Andrew. I did mention that there is actually a simulator if people are interested in understanding how dispersal of plastic happens in the ocean. So, people have heard about these garbage patches, but there is a really fun simulator, and it goes back to, it's an online simulator, Rubber Ducky Ocean Simulation Dispersal. And I'll tell you why I use the word rubber ducky. So first of all, I don't know, it was a bad thing, but this is the reality. There was a massive shipping vessel that was heading out to sea, and it was carrying our favorite toy, billions of them, and it flipped over and it dispersed accidentally. It did the largest, what you can think of as an ocean dispersal experiment by accident. And still, from years and years, so it was 4.7 million tons of plastic is dumped. No, I want to get to the, this is the simulator, but where is my numbers on the rubber ducky? Okay, it's inspired, but it doesn't actually talk about the, okay, here is what I want to show you. But before that, rubber ducky ocean accident. Okay, so 28,000 bathtubs, 1992, lost at sea. And then people started reporting them. It's like, hey, my beach. It was a rubber ducky that showed up. And from the make and mock, people started mapping. And this became, and by the way, it's a beautiful book. This became the best tracking technology that we had for ocean currents. Because as I was saying before, simulations you can make plenty. How do you validate it? Without measurements, you can't validate it. So this would be totally illegal to do, but it just happened. And then this simulator is inspired from that. So the simulator that I just opened up here, I remember that. Let me see if I can find the map that allows to simulate. No. I have to find it, but there's basically a simulator that you can put in and virtually drop some rubber duckies. And do you know the link? Just put it on Slack or somewhere on Discord. People can take a look. So I think, one of the important things to try to remember is a little bit about, without measurements, many of these simulations can't really have the kind of impact. So I'm going to just spend a few minutes on measurement technologies because this is what we'll be focusing on the lab. We'll get some water tomorrow, and we will show you one technology that we've been working on. Any of you can also extend this technology, but let's just walk through in terms of thinking about it's so large, it is an issue in how we measure. And let's essentially take a look at a couple of measurement techniques. So the first is the satellite. We talked about this. You can measure chlorophyll. These are maps that are published. If you go online, for last month's chlorophyll maps might be available. You can get higher resolution maps locally for certain sets of places. This is one classic tool that essentially exists. As a function of time now, this is not simulation. This is over a period of time, purely chlorophyll concentration. So this is kind of one of our best ground truths that we have for biological measurements in the ocean. One of the things that starts to happen is associated with these types of things. There is also a very large number of things that you can start collecting, including winds. There is phenomenal data set on wave height that can be measured also with sets of tools like these. And again, at a scale of the ocean, this is quite frugal because you get a whole picture in one shot. So all those satellites and those sets of programs have a cost associated with it. Now, this is what I want to spend time on. These are a class of these tools called Argo floats. Now, not so frugal, but there was a program that started some time ago. Many groups put together this buoyancy engine. If I was standing next to it, it would be that tall. It's a cylinder that big. You can put any gadgetry that you want in it. It has a buoyancy engine that it can be pre-programmed to go up and down at a known depth. You could put temperature sensors, light sensors. You can put whatever you want in it. There is power. And then it has an Iridium satellite right up there. So when it comes up to the surface, it will get the data out. And then after, X amount of lifetime, which can be a few years, it sinks to the bottom of the sea, adding to the problem of ocean pollution. Now, that's the number of Argo floats that we have launched so far. And currently, this is the best network we have for ocean temperatures, for example. So the reason we know so well that the ocean temperature is rising is because of this network. It doesn't do any biological parameters as yet, although people are currently building. So the reason I'm mentioning this is that there does exist a platform that you could incorporate your idea in. Say if you came up with, I want to measure this particular metric, say a biological metric, that gadget that you make can actually go reside inside this. And the rest of the power communication, you don't have to deal with. It's a platform that's readily available. Anybody can build on top of it. There are official Argo floats. There are also unofficial Argo floats that are tested, but a phenomenal platform. The only problem is it costs $75,000 per float. So that's a massive investment also. And again, I asked myself, why should it cost that much? And some of that is just, again, driven by, could you build and design a buoyancy engine that would be very... So does everybody know what a buoyancy engine is? I'm just using that as a term. It's a gadget that if you program it in a certain way, will change the buoyancy or density of an object, that it will naturally go up and down. So for example, if you take a reaction that makes gas that suddenly changes density, if you could trigger that in a controlled manner. So submarines use things like these. There's many types of buoyancy engines. And then this is just using a robust buoyancy engine. Yes?
I was gonna ask, you mentioned that ingredient
Mhm.
satellite. Could you elaborate on the difference between that and GPS satellite?
Yeah, I think it just is there is a massive class of communication tools that have become available. In this one, we really deeply care about getting data out, because if this thing sinks with all that investment and we got no data out, so you could go live online right now on Argo floats. There's also a really beautiful program called Adopt a Argo, because they make it look like minions. And then people care about them. And then you monitor, you say, my Argo float is not collecting data, what's going on? There's a beautiful online program. But the purpose of that is just, Iridium is just our best high bandwidth. And even that bandwidth is low for imaging data. Like, we collect a lot of imaging data, so I couldn't put planktoscope, which I'll talk about, for example, in this platform, because we don't have enough bandwidth to get data out. There's a couple of companies working in this space, and one of the challenges is low power, high bandwidth communication. It's the same problem in space per se. Doesn't have that many commercial applications. Starlink and other factors have a totally different route, but then on the other hand, the infrastructure required is, I think sailors, for example, are starting to get more and more interested in getting bandwidth at sea. That might lower down the cost of it. And I think, yeah, if you're excited, I can send you, somebody just shared with me a cost profile to see what is the projected, because you might be designing a technology and you want to see 2 years from now, how much is it going to cost me to send 1 bit from in the middle of the ocean to my laptop? And the projected costs are going down, but they're not like what you'd often see in telecommunication. Like what happened with cellular, if you look at its cost, is just plummeted completely. That's why we watch movies on our cell phones. Nobody buys DVD anymore. It's just because of that. But that hasn't happened for the ocean yet. Yeah. Okay, so I think this is Argo Float. Yes. They run out of battery. Yeah, and it's designed then to sink to the bottom. It's a very obvious thing, like, why don't we just collect them? The cost to go out there and collecting it would be higher in fuel and also the CO2 released, and that it's better to just let it die. And it's a very small portion of the total things that we're dumping. Nobody feels good about dumping them. Lots of people have been, phenomenal project idea. It's like, okay, I'm gonna figure out a low-cost way to collect my Argo back. Yeah, but I think currently they have just a certain amount of life. You could think about, there are some gliders people are making that are low power, some amount of, solar and renewable, but its footprint out, because its measurement happens, this does go down quite deep. So most measurement it makes is in the dark. So it's not as if you could just rely on solar. There was a comment/question. Yes. Yeah, I didn't know you guys would be so interested in the Argo, so I have to now show you the website. I'm just doing a review just for, so that's what happens. You take an Argo. I've thrown one before. It feels kind of, there we do ceremony when you throw something in. But again, these are instruments and your instrument might be in there. It'll remain like 6 to 12 hours at a surface. It's transmitting data. You can program that. It'll descend. So now it's at 1,000 meters and it'll drift. And it's very important that the kind of the sets of scenarios so you can also get underwater currents, because you can make estimates of currents up there. How do you know the currents that are going in a completely different direction? All of that is critical for our models. Effectively, it can come down all the way down to, actually, it goes all the way down to 4,000 meters, if I remember. It'll do a profile when it's rising. It'll give you a profile as a function of time. It's rising very, very slowly, so it's not perturbing the ocean that it is measuring. But again, it's a very important, different approach than what I said about going on a vessel that's costing $50,000 a day. And this will continue to operate. Here is the cost. The core, just the core itself is $20,000. You add wings and fins, a couple more thousand, roll and pitch, 5,000. And then the entire thing ends up being like $100,000 in terms of just the package. And then again, you know, there are thousands of them. So it's a massive investment. And again, thinking about, if you say, hey, I want to take this and think a completely different approach, but reducing the cost of these instruments would be a massive win in what we could measure. And again, you know, I think some of that is driven by how dense we can actually do this. And I'm going to pull out a Argo float for you guys, just so that you see it. Argo float live. Let's see what's in our California waters. Oh, come on. Click the map to see. It's always hard for me to. No, I want the live map. Live map. There is a dashboard. Okay, does anybody see a dashboard? Data. Okay, Argo dashboard. Okay, Argo track live. Okay, I'll find and share it. There is really a fun dashboard that you can all play with. And I often look for some floats in our local waters and say, oh, this one is not responding, and it's right close to some of the times when we are close to a boat, for example. There was a question somewhere. Yes. Yeah, I don't really understand that. I think the thread that I know is that the recovery cost is actually a significant amount, because you can go out there and not find it also. Because most of the time, all you see is the time. I mean, the most important lesson that you probably learned when you were at sea is, if somebody falls overboard, you have to be looking at that person continuously and keep pointing at them. That's because you are a very tiny, and keep shouting. No matter if they are right there, you still cannot let your eyes off, because most assets that we put off board, the waves are so big that you don't often see them. So actually, I mean, I think people have been thinking about better recovery. If one of you gets excited about recovery, we can then talk about other sets of ideas, especially recycling, refurbishing old Argos to upgrade new sensors would be a big deal. But I'm sharing the challenge. It is quite difficult to recover assets at sea. Yeah. Okay, let me just jump to one more of my favorite historic tool. This has been an inspiration for a lot of work that we have done in the lab. This is an object. It has no batteries. It's just made out of, machine metal. And it's called a plankton recorder. And it's one of the oldest running, kind of more citizens oceanography oriented instrument. And it is very strange. what is inside this object is a massive reel of silk. There are no batteries, there's no electronics, nothing. It has a tiny hole here, and you attach it to the back of a ship. So lots of shipping vessels are going out there that are regularly converting traffic. Like, they're carrying our goods, our computers, every possible thing. And so Alistair Hardy, who's a phenomenal oceanographer, came up with this idea: what if zero battery, I could just attach the passive thing that these people could tow. And what happens is that there is this massive mesh of silk, 2 plates that roll because of the flow. So the power comes from the flow itself, and it seals all the biological objects that are flowing through that because it's a mesh. It lets the water go through and it filters, but it also keeps rolling. So it's a tape recorder, but it's a tape recorder of life, microbial life at sea. And when you come back, you essentially get these tapes, and it's worth just seeing it in action. Not that. Maybe we should buy the YouTube, the version that doesn't give us ad. Dismiss, please. Oh, come on. Okay, here it is. What's this one?
Century in the UK, it was kind of hard to know where to send the fishing boats, where they were going to find the herring. And Alistair Hardy, he invented this instrument that could be towed behind ships, measuring the plankton, and it's called the continuous plankton recorder. Continuous because rather than taking a sample as a snapshot across, it continuously samples the plankton as it goes. So his idea was that if you could understand the food of the herring, food of the fish, maybe you could.
So you get the idea, right? And then plankton recorder. I just want you guys to see what so there is roughly around 100 or so at sea. People have been thinking about automating some of these too, and I'll talk a little bit about that. But I wanted to show you guys what these rolls look like. Because these rolls are kept and then they are manually read. Is that the rolls? That's the archive. That's how we keep our planet's history in Tupperware. But you could go in there and say, from this year to this year in this transect lies a piece of silk that has, this is hundreds of miles of a transect. So it's actually a very long transect, all in that piece. We still read this manually. So one thing that I've been thinking about just as a project idea is to automate much of this, that even going back in the archive, so we truly even understand 50 years ago, what did the diversity and the biodiversity actually look like? Because here I can identify a specific organism. This thing has a chemical, so it actually fixes. So again, I love this instrument, and I think some of what we did was inspired by this as a tool. And again, you might think, why is it that these archives are important? Why do we want to go back and read? One thing that's been really phenomenal is people in even the 1870s. This is the HMS Challenger, a very famous expedition. These are foraminiferas. They were stored. You can go back and now do a CT scan, and then you can do one CT scan from a sample from 2000. And this is what shows us that the ocean is acidifying. So what's happening is this is biomineralization as a process, which most likely is calcite in this case, is affected by the pH of the ocean. And now the same organism cannot synthesize enough shells. So a lot of snails in the ocean are actually in big trouble, because effectively the biology is not adapting fast enough. But this is very much like, fossil records that you can go back, but back calculate the chemistry of the ocean. So this is why technology is just going back in terms of these archives and reservoirs is actually very important. So just in terms of project ideas, there is lots of tools that are out there. This is a breadth of size scale in the ocean that matters in the biological pump. Everything we need to be measuring viruses. Benedict was just hinting towards an idea that we've been thinking about to do a low-cost viral detector using imaging, which is kind of a challenge because viruses are often below the resolution limit, but there are tricks that you can play. All the way to a very hard thing to measure is, I don't know how many of you have swam around in a pool of jellies. The biomass density of some of these salps is very difficult to estimate, but they also sequester a tremendous amount of carbon, just because when they die, this gelatinous matter actually takes the carbon. So I think maybe the thing that I did not mention, if it was not so obvious before, was the biological pump operates on a simple principle in which as the organic matter in the ocean dies, it sediments. And then when it sediments, it actually collects, and it collects at the bottom of the sea. So I had this picture, but I didn't say anything about it. Does anybody recognize from a movie what that is? Huh? Yeah, it is Mountains of Dover. That's correct. Or the Cliffs of Dover. It is a testament that, I feel very positive every time I see this. The entire mountain, so if you were standing here, your length scale would be like that big. This truly is a mountain. But it's white because the cliffs are made of single cells that are less than 5 micron. But over thousands of years, them dying to the bottom, and this is how carbon sequestration works. So this was all under the sea, and then the organism that the Mountains of Dovers are made on are coccolithophores. And that's the organism that essentially makes that. And the scale bar of this is 5 micron right there. And then every one of them essentially sinking and falling over years is what, in a given point, that sedimentation is. And at the bottom of the ocean, that's happening the entire time. So very simply put, carbon from the atmosphere dissolves in the water. That dissolved carbon is taken up by biological matter to make its biomass, because all life uses carbon. When it dies, and also this is calcite, so one of the threads, calcium carbonate. When it dies, it'll sink, and if it sinks, it'll actually take and sequester that carbon. And I think the number is, if you can sink below around 500 meters, you have locked carbon for around 1,000 plus years. So you don't have to worry about it. That's why tons of companies are starting right now wanting to dump algae and kelp into the ocean and make kelp farms and claim carbon credit. Although it's not as simple, because when you dump something in the ocean, the bacteria come along and says yummy food, and they eat up all of that, and then they release all that carbon back. So if you don't understand the biological process, none of that makes sense. And this is why I'm kind of saying that although there are all these optimistic stories that are told, we really don't understand what would it mean. You can't dump iron in the ocean and just claim that you're going to get positive carbon flux. Question? Yes.
I have a question about the kelp that you were saying.
Yes.
I often hear kelp being used as an example of ocean CDR, and people are very optimistic about it. But I've never,
I don't.
Okay, yeah, I've
Yeah.
never been given an actual number for its potential or an experiment or study done on how much carbon it can actually sequester.
Mm-hmm.
Is there any papers that have produced?
There is tons that's been written, and I think I have an opinion. We need a broad range of ideas. I think that's all great. We should be in the idea space. Secondly, we need really good by the number estimates. Just like the exercise that you're doing, people should just publish the sets of by the numbers. But in most of the things, in the projection that we all have as technophilia in our society, we don't want to sometimes look at the reality that we don't understand the biology of the ocean. So although at this moment, there is a VC around in 5 miles of you at this moment who would be willing to give you a ton of money on a claim of like, hey, I'm going to make ocean CDR work this way. There's very little money when I'm going to go and say, I want to understand the current world's best sequestration technology that's currently operating at scale, which is the biological process itself. And anything that you're going to change, you have a much deeper understanding. So I think it's the attitudes that change in some sense when you talk about these. Both are necessary, both must be done. I'm kind of the camp that measurement is the key. If you improve measurement technologies, I would have a better estimate for what is okay to do even at ecological scale, at larger scale. The level of ethics that you can bring in these types of problems will be far stronger because somebody would be held responsible. Like, this is not working. Let's stop and try something else. And many of these technologies are being proposed in the sense that, oh, and hence we can continue doing what we're doing. That's a big problem because neither are we solving the problem by actively shutting down some things that we should shut down, nor are we actually talking about real solutions. So it's a double whammy in some sense. And measurement is at the heart of both of them. I think there are some numbers. I know of a company or two that have come and reached out to us sometimes to do some measurements for them. It is a moving space, but the biggest mystery in all of that is really the bacterial decomposition. The bacteria play an incredible role in whatever you dump in the ocean, and they bring that carbon back up because they just want to, it's free food for them. And again, it's a dynamic system, so much harder to tackle. Yes. Yes. Solar panels for Argos. That's a fantastic idea. I haven't seen a solar panel. I think it has to do with a little bit of the cross section, but imagine a folding solar panel that when it comes to the surface, it would have a larger area, but when it dives back in, it kind of refolds back. I think, you know, the system can't be delicate. That's the one important thing to think about. And then the other question was, would it be easier to retrieve the Argo if they floated to the surface when they, you can make them float to the surface, but that doesn't make it easy. I think one of the challenges is finding stuff in the ocean is pretty damn hard, even if it had a GPS coordinate. So there are sometimes assets that we deploy which has a GPS on it, and I know it's there. I can see it on the GPS mark and on a boat, and we don't see it. So I think something else is needed, but, you know, some kind of a homing. But again, you know, as you already said, navigating the ocean and complete autonomy is also very difficult. Yes. That would be the right direction to go. Yeah. 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 And again, you know, I think it's a trade-offs between the cost. It is important for it to be a small form factor. And currently, this is one of the big limitations in the scale of the Argo program, that if they truly were much more long-term, if we could make an Argo float that's going to survive 100 years, then people would be even much willing to put a larger, like an order of magnitude more. I know some of you have to run. Maybe what we'll do is I will do a quick review in the lab tomorrow of what we've been working on. And then tomorrow's lab is on oceanography measurements. So try bringing some water tomorrow that you want to measure. And, you know, don't bring it just from home that's drinking water because you're not going to see anything. Like some mucky, murky water from a pond nearby, something that you felt, hey, should I drink it? Don't drink it. Bring it here, and we will do a monitoring of it to see what we can measure. So that's kind of an exercise. I'm going to close just to make sure that for folks that have to run. And in terms of the folks that are online, I would like everybody to read this paper or just go to this website. planktoscope.org. This is the instrument that we built. It has all the instructions for not just how the instrument works, but how to build it yourself. So you can see instantiations of them being built by people around the world now. And there are many, many instruments that are starting to pop up. And then if you go in here in documentation and assemble your kit, all the actual instructions of building the instrument are online. And so you'll see every little detail of how to put this instrument. So I know many of you won't have this physically in your hand, but what we'll end up doing is as we run sets of demos, you should walk through and get a sense for what are the intricacies. And then if some of you end up deciding the parts, it'll take a week or two for someone to assemble it. But if a team ends up deciding that they really want to build a solution on top of this, and then if it happens to be a team, an international team, then I'm going to figure out a way to send you guys all the parts. But just first take a look at it. And then there is a new tool that we literally released yesterday. It's called Espresso Scope, which is kind of a mini version of right there. It has a mini version of Planktoscope 2, which is now all completely 3D printed and also much, much easier to assemble. So I'll also talk about this in the lab tomorrow. But I think, yeah, these are two little assignments before you come to just read a little bit about the Planktoscope, because we'll spend a lot more time using it, and read a little bit about Espresso Scope. The version that does plankton imaging is, something like this. It's much, much simpler, much smaller. Doesn't do the same thing, but it's useful to know. Okay, I'm going to stop sharing, and then we'll turn that back to what we do in the end of just open time for questions, any clarifications. And folks that have to leave can leave. That's not an issue, but we'll do an open mic time today. If you have ideas that you're starting to tickle your mind for a project, I'm here. We can talk about them. Okay, thank you. Yes, Henry. I just got a message last night that I have to give my due dates. It's for the first time, it's going to be out of San Francisco. It's going to be on the coast, and it's May and June. It's 45 days across the Pacific coast. And this is something that we've been planning for 4 years now, but it's about to happen. If any of you are in the area and want to see the boat, it will be docked in San Francisco. I'm happy to show you guys the boat. It is on Kilo Moana. I can't guarantee if I can bring you on the boat, but most likely for a short time I could. If you're excited, do send me a message. Just remind me, essentially. Yeah, it's going to be from the port in San Francisco. And we will also have a port stop. So we'll have a crew exchange. So because it's on it's a coastal cruise, which is much easier to do, we can do half the cruise, we can dock, we can swap teams, and then we continue the cruise. 45 days it's tough. So yeah. Any other questions? And then I'm here if people have interest in wanting to talk about projects, because slowly it should become, we should just get excited about things that you all might want to do. And I'm here to kind of give feedback. If you want to book time on my calendar, now would also be a time to just do one-on-one sit-downs. If you're starting to talk to friends to say, let's build a team around, that's also a good idea to start doing that now. Does anybody have they're absolutely dead sure they want to do a project in a certain space? No? Nothing yet? Yeah, what do you want to work on?
I want to work on biologging,
Mhm.
and more specifically, reducing the cost of something like whale trackers
Mhm.
and improving their overall performance.
Mhm. And then, so in terms of, I think narrowing the focus would be phenomenal. So you can be thinking about ocean and whales. That's great. You can look at everything that's currently there. But I think one of the threads to also think a little bit about is not to get trapped in the current class of solutions also. Because it's one thing to take an object and say, hey, how do I reduce the cost tenfold? It's another thing to say, wait a second, I'm going to think about this problem differently. And because of that, I reduce the cost. So just in that early phase, but the problem, is something that you should choose early. Yeah, no, I think that's fabulous. I would be very happy if we have some ocean-oriented projects. Anybody else has a tingling idea? Anybody online? Go ahead, Pavan.
So I was still fascinated by the thought we had from the previous class, which is regarding the X-rays from the tape.
Yes.
I just found it fascinating. It's something which is a thread which I was interested in pursuing. I've not decided. I was still reading up the literature, and so there are many patents by the first authors which they've built on more and more, but nothing has so many publications. But they just have characterized more on the X-ray frequencies and so on. But I don't know. I thought
No,
it was
massive
worthwhile to try.
amount of space there. And
Yeah.
frankly, because the original paper, the original Russian paper is also there long time ago, it's, you can only patent a specific material. You can't patent Scotch tape.
Yeah.
That's taken.
Mm.
So in some sense, there is a massive intellectual space there to think about. But I think the important aspect is, and we can talk separately because I have a MD PhD student here, and we've been working slowly towards the notion for TB. That's the space that we identified would be ideal. And so if you get excited, I'll involve him as well. But you should just independently think.
Yeah,
And
I
an
was just
important
reading
thing to
up,
think about is try finding an application in which the X-ray dosage and strength, very low X-ray dosage and strength is useful. That's the key, because there is a fundamental limit in how high the intensity gets. But again, for a lot of medical applications, you don't want high intensity.
Yeah.
Yeah. Yeah. I mean, I would be
No, because
thrilled.
they do demos in the paper where they do create an X-ray using the dental X-ray sheets.
Yeah.
And they do have a finger like X-ray. I'm like, this was
Yeah.
like 15 years ago, and
Yeah.
nobody
Yeah.
seems
And
to have
for
done.
and for the class project, getting to a point that you immediately also replicate that by itself is phenomenal. Literally, a $10 pump, some Scotch tape and a motor, and a dental X-ray plate, you should be able to replicate that result. And this is the spirit of the class too. Like, don't wait for your end project and, oh, I'm going to spend time designing. Then you won't build anything in the class. Then we might have as run this class in a lecture room and not in the lab. So at some point of time, I want you guys to feel that there should be an urge and an itch to make something. It's not your final project, it's not, but you are actually making stuff. This is why also the CAD part was important, because we can show you thousands of examples of what we work on and do, but unless you kind of feel like, oh, this is what I created. So in the lab, anything you create, bring as a show and tell in the lab session. Even an awesome food dish counts. I think have to be in that spirit of wanting to create something. Art pieces, whatever you create, do bring a show and tell. And especially if you're working on a side project, you might say, hey, I want to 5-10 minutes show you what I've been working on. It could be your thesis project. It could be something else that you have made in the past. I really want to start transitioning from, I think it's important to just show you all a few sets of case studies, but if we just end the course with case studies, you might as well read all of this. So it would be very valuable that people start doing some show and tell. Niam, go ahead.
Hello, I'm still really interested in the microplastic
Yes.
pollution problem. But what I would really, really love is to make some kind of either a detector or a sampler. I don't know whether I'd like to measure microplastics optically or through sampling, but something that we can explore. How cheap can we get? How simple can we get? Something that people could make with stuff in their house, maybe. And then if it was a team, if we could replicate, like I'm in Ireland, if we could replicate it in different countries, you know, that would be just proof that it works.
Yeah. Yeah. And I think one important thing to think about is, Niam, take a look at the espresso scope paper that we just posted. We built it with parts that all of you have, and it might be that for all the international teams, I might ask you all to just build them because we are just testing. We worked very hard to make sure that that platform is anybody can start building. And if it ends up being, you've already built one.
Yeah.
Oh, that makes me so happy. Wow. I mean, of course, we had released the documentation, I'm assuming. How did you find out about it?
I know I've met Benedict before through conferences.
Fantastic.
Yeah.
Fantastic. Okay, so you've already built it. Why don't you bring it tomorrow and show people? And then one thread that would be useful is a microplastic detector on top of that would actually be really fun.
Yeah.
Yeah, yeah, because there's a lot of work that Benedict did on the software side of that story that's really scalable at this point. And I think, you know, the resolution and sets of things can all be validated and changed. Yeah, no, I mean, that would be fabulous. And especially also thinking about not just the ocean, but our freshwater streams also.
Yeah.
And, you know, I think for some of the folks that are in India, both lakes, water reservoir, but our river systems have no monitoring at the small scale. So it's the same idea that applies. Okay, any other comments, questions? Yeah. Yeah, yeah. Yeah, and you want to find a good use of it.
Right.
Yeah. I think there's a couple of ideas that I have that we can talk about. One thread really is that in terms for a lot of automation, there's a huge issue around how we manufacture, because in these compliance systems that can go away. There is a project that we are working on in the global surgery space that I could tell you about. Surgery, 5 billion people on the planet don't have any access to surgery. Like something that you take for granted, like a very simple laparoscopy, gallbladder, significant portion of the world don't. And again, some of that boils down to laparoscope, some of that boils down to, you know, just there's a massive space in surgery in some sense. There is another class of things in terms of when you're trying to build, say, a lot of underwater systems. And I think the challenge there is you have to take everything that works pneumatically, but operated with oil. You can't get compression underwater. That would just be disastrous for the deeper and buoyancy itself. That would actually be another space. There is a little bit of work people have done in soft robotics applied to sampling, that when you have deep rovers that go down to very gently collect stuff for analysis, but it's a niche problem. It's not it doesn't really crack. Yeah, let's chat. I think making much more of also a platform where some things that you would traditionally do using motors and other things being completely replaced. Like weight is a huge advantage. Some time ago, one team tackled in the class a space debris problem. And that was, so just the problems that you work on don't just have to be relevant to Earth, by the way. So Nesta's team in the first year tackled the problem of how to capture space debris because the cost per unit capture of space debris is insane. And they actually used kind of ideas in soft robotics and also just soft materials per se. Yeah, I'll send you that presentation. Yeah, yeah. Okay, any other comments, questions? Otherwise, I'm assuming on Discord, you're all starting to fill the channel that talks about the ideas, right? So even if you have a vague idea, just post it. It's much more important for you to have other team members be excited. Otherwise, if you don't recruit somebody, it's tough to work alone. I think ideally recruit 2-3 people to your team. 3-people team is just the right ideal circumstances. So just if you don't share that early, then other people might not see it soon enough. So Niam, if you have kind of a framework on the plastics, you really are excited, write a Fred Park, share it in that, name your team early on, just so that it's like, oh, we're starting to build a connection so that you can at least recruit 2 more people. Okay, I'm gonna say bye. And again, sorry for being late today. I really want I can't say that I want the rain to stop in California. That would not be good. Okay, so yeah, bye everyone. I'm just looking at the Discord now. And are there anything on the project ideas yet or no?
For project design board.
Yeah.
I think they spoke about it today. There's not too much, but we made an announcement just now.
Yeah, so one of the other things to do it is we could also do it via Notion as a more formal design board.
Yeah, I need
You saw the last one, right? We have the Notion page.
So I need you to add me to the Notion.
Excuse me, Professor. Hello. Professor, am I audible? I think you are muted, Professor. I can't hear you. I wanted to talk to you for a minute. I can't hear you, Professor.
How do I do it?
Yeah, now I can hear you.
Oh, yeah. Now I removed the microphone.
Vaibhav, send me a message on Discord.
All right, Professor. I will.
Yeah? Okay.
Yeah.
And I'll send you a time.
Thank you, Professor.
Notion.